Good morning. My name is Spurti. I am pursuing BTech first year in EEE department at IARE College. My course title is Electrical Circuits. My presentation title is Kirchhoff Laws and Graph Theoretic Circuit Analysis. Introduction to Kirchhoff Laws and Graph Theoretic Circuit Analysis is Kirchhoff laws are fundamental in analyzing electrical circuits. Graph theoretic methods provide a systematic approach to circuit analysis. Combining these techniques enhances understanding and simplifies complex circuit problems. Overview of Kirchhoff laws. Kirchhoff laws consist of Kirchhoff's current law and Kirchhoff's voltage law. There are two types of Kirchhoff laws. One is Kirchhoff's current law and another one is Kirchhoff's voltage law, which we can also call as KCL and KVL. These laws are based on conservation of charge and energy. They are essential for deriving equations in circuit analysis. Kirchhoff's current law. Here is a picture which describes KCL. KCL means sum of the currents entering a node equals to 0 or sum of the currents leaving a node equals to 0 or sum of the currents leaving equals to sum of the currents entering a node. Here is a clear example with a diagram. Kirchhoff's current law states that algebraic sum of currents entering a node equals to 0. As we know just now, same the definition is it states that algebraic sum of currents entering a node equals to 0. It ensures that charge is conserved at junction points in a circuit. Yes, KCL is used to write current equations at circuit nodes. So it helps to write current equations at different nodes. Here is a diagram which we can solve by using KCL. KVL, Kirchhoff's voltage law. KVL states that the sum of electrical potential differences around any closed loop is 0. So potential difference around in any closed loop is equals to 0. It states that potential differences in any closed or enclosed loop is equals to 0. It reflects conservation of energy in a circuit. KVL helps in establishing relationships among voltages in loop. Circuit representation using graphs. Circuits can be represented as graphs with nodes and branches. Nodes correspond to circuit junctions, while branches represent circuit elements. Branches represent circuit elements. Nodes represent circuit junctions. Graph models facilitate systematic analysis of complex circuits. Elements of graph theory in circuits. Vertices. Nodes. Vertices means nodes represent connection points in the circuit. Edges. Edges means branches. Branches represent circuit elements like resistors, capacitors, and inductors. R R means resistors, C means capacitors, I means inductors. Edges represent these three circuit elements. The orientation of edges can be assigned for analyzing directed flow. Incidence matrix in circuit analysis. The incidence matrix relates nodes and branches in a circuit graph. It indicates which nodes are connected by each branch. The matrix is useful for formulating KCL equations systematically. So here we can see a good example for KVL law. By here it is shown that VPQ, voltage around PQ plus voltage around PQR plus voltage around RS plus voltage around SP is equals to 0. Fundamental loops and spanning trees. A spanning tree connects all nodes with the minimum number of branches. Fundamental loops are formed by adding one branch back to a spanning tree. These loops are key in applying KVL efficiently. Applying Kirchhoff laws with graphs. Graph theory simplifies the identification of independent loops for KVL. KCL equations can be derived from the incidence matrix. Combining these approaches streamlines complex circuit analysis. Coming to mesh analysis using graphs, mesh analysis involves writing KVL equations around independent loops. Here we can clearly understand what are mesh analysis problems by the picture I have placed here. Graph theory helps identify these loops systematically. It reduces the complexity of solving multiple simultaneous equations. Nodal analysis with graphs. Nodal analysis focuses on applying KCL at circuit nodes. Graph-based methods help organize node equations clearly. This approach is especially useful for large and complex circuits. So these both nodal analysis and mesh analysis plays a vital role in Kirchhoff laws. Coming to matrix formulation of circuit laws. Circuit equation can be expressed in matrix form for computational efficiency. The incidence and loop matrices are used in these formulations. Matrix methods facilitate computer-aided circuit analysis. So here are some examples for circuit analysis. In circuit analysis, there are two steps. three steps. Here is the step 1. Identify all nodes and branches in the circuit. The first step we should do is to identify. We must know how to identify nodes and branches in the circuit. Assign directions to currents and voltage for clarity. After that, we must assign some directions for currents and voltage by representing a arrow mark by which we can get a clarity. Construct the circuit's graph representation accordingly. Example circuit analysis step 2. Here is the step 2. Formulate KCL equations at each node using the incidence matrix. Now, at each node, we must apply the KCL law and write the equation. Now, write KVL equations for each fundamental loop. After writing KCL equations at each node, we must identify loops and current and voltage directions by which we can write KVL equation clearly. Combine these equations to solve for unknowns. Now we must solve these two equations and find unknowns. Now step 3. Solve the resulting system of equations using algebraic methods. Check the solutions for consistency with physical laws. Interpret the results in terms of circuit voltages and currents. After solving that, we get what is the current, what is the initial current, what is the I1, I2 which may be further existing, what is the voltage, initial voltage, what is the V1, V2, and we can clarify, we can get resistance if there is a resistor in the circuit, by which we can find unknowns. So, coming to advantages of graph theoretic methods, they provide a visual and systematic approach to complex circuits. Graph theoretic methods provide a very visual and systematic approach to complex circuits. Graph methods reduce the potential for errors in deriving equations. These techniques are adaptable for computer algorithms and simulations. So, limitations and challenges. Here are some limitations and challenges which will be taken place. Large circuits may result in complex and large matrices. Yes. Proper assignment of directions and reference points is critical. Graph methods require understanding of both circuit theory and graph theory. Practical applications of Kirchhoff's and graph theory. They are used in designing electrical networks and power systems. They are applied in electronics to analyze integrated circuits. There are many applications of Kirchhoff's and graph theory, but here are few. Essential in communication systems and also in signal processing. Here we can know there are three mainly applied Kirchhoff laws and graph theory circuit analysis. First one is electrical networks, power systems. and it is also applied in electronics in to analyze integrated circuits, also in communication systems. And coming to the summary of key concepts, Kirchhoff laws are vital for analyzing electrical circuits. They play a vital role. Graph theory provides a structured approach to a circuit analysis. Without graph theory, we may not understand a circuit clearly or clarity. Combining both methods enhances accuracy and efficiency. Conclusion and further reading. Here is the conclusion. Mastery of Chris- Kirchhoff's laws and graph theoretic methods is essential for circuit engineers. These techniques form the foundation for advanced circuit simulation and design. Further study can include software tools that implement these graph-based analysis methods. Thank you.